Hello, here's our part 2 of our complexation discussion. So we've already talked a little bit about an overview of what complexes are, or complexation, and the first type of complexes, which are the metal ion coordinate complexes. So now we're going to start talking about the molecular complexes, which the reason this is different is because they're held together with non-covalent bonding versus covalent bonding. The first of these types that we're going to talk about are cyclodextrin complexes, and those are those donuts I was showing you pictures of earlier. So, okay, we'll talk about cyclodextrin if I can forward the slide. So here is a picture of our cyclodextrin, and as you can see, it's a donut-shaped molecule which can hide drug. I kind of think of it as like the cloak of invisibility if you're a Harry Potter fan. The surface is hydrophilic, and the cavity is nonpolar, so that a drug that needs to be in a hydrophilic system, it can hide in here and become more soluble when you add these little donuts into the situation. So these will allow like several things to be better. It will improve the aqueous solubility, and again, this is what that cyclodextrin little donut, the invisibility cloak, looks like. It can make the drug more soluble. It can make it more stable. It's not going to be as easily broken down when it's being hidden inside this protective coat. It can improve absorption, and it can improve taste. It also can decrease the side effects of the drug. So these cyclodextrins are very useful, and there's several different types that we use. So as we increase the number of the donuts available, so here's our concentration of beta-cyclodextrin in a solution. So as that increases, as we add more of those donuts, so here we have from 0.5 to 2 millimoles per liter of the donuts, we're going to see that our drug concentration can also increase too, because we're increasing the solubility, right? So as we add more donuts, our drug concentration can be increased because we're increasing solubility. So we can plot this, can't we? Our CT is our concentration of drug, or I'm sorry, is our increasing concentration of our beta-cyclodextrin. Beta-cyclodextrin, or cyclodextrin, is increasing as we move along. Move along this. What am I doing? Yeah, as we move along this x-axis, increasing the number of donuts that we add, we're going to see an increase in the solubility of our drug, aren't we? So it's a positive correlation. As we increase the number of donuts, we'll be able to get more drug into solution. Now, that relationship is described by this crazy equation. So our drug at any point, our drug concentration at point T, will be equal to our drug concentration when there's no, this is a 0, because there's no cyclodextrin in here. So that's our y-intercept here, right? Because this represents a cyclodextrin concentration of 0. So this is our innate solubility. So this is what the drug solubility would be, the maximum concentration you can get into solution before you start adding beta-cyclodextrin. So that's our innate solubility, D sub 0, drug concentration without any beta-cyclodextrin, times this big relationship, which I'm not going to get into, but you can see it includes our innate solubility and our Ka, which is an affinity constant. Remember, we talked about the fact that every system is dependent upon affinity and capacity. So we have an affinity and capacity component here. Capacity is how many of these donuts we're going to have in here, right? That's going to be the capacity of our system. Now, it is arranged this way because it's linear. You know the equation for a line is y equals mx plus b. Well, that's the same arrangement here because our y value is our drug concentration, isn't it? And our X value here is our beta-cyclodextrin concentration. The slope of our line is represented by this big whole equation here. So this slope is determined by this relationship here. And our y-intercept, as we already determined, is going to be our innate solubility, isn't it? So this is the equation of the line that describes the relationship between our drug concentration and our beta-cyclodextrin concentration. And we're going to use this relationship to solve problems. This would have to be given to you. I don't expect you to know this. This is given. And this is given. We know, I mentioned that our affinity constant, which is represented by Ka, is going to be equal to the slope. Again, it's this big piece here. The sum total of whatever our slope is, which is determined by this. We can put our slope into the numerator here. It's also part of the denominator, so we have our slope divided by our innate solubility, which will be our y-intercept, times a quantity 1 minus the slope, and that will give us our affinity constant. So if we know our slope and our y-intercept, we can determine our affinity constant. So here's an example. We have, again, at a 0.5 millimole per liter, here's another drug. It's called para-aminobenzoic acid, or we'll call it PABA. PABA concentration will be 1.74 millimoles per liter when you have a 0.5 millimole per liter of beta-cyclodextrin available. So this isn't the innate solubility, right? It's going to be less than this, isn't it? And then we have data pairs all the way up to 5 millimoles per liter. So we can plot. This would be, let's go back. What's our beta-cyclodextrin? Our beta-cyclodextrin concentration is our X data, and our Y data is the resulting drug concentration that we have. So X, Y data. We could plot all this data, and we will get this. Great. So now we know the relationship, and makes a nice straight line. It's our beta-cyclodextrin concentration versus our PABA, our drug concentration. So you can see it's a nice straight line, and if we use our computer or our calculator to run a line of regression, we get the representation that y equals mx plus b. M is our slope, and b is our y-intercept. So now we know y is our intercept, and b is our y-intercept. And so now we know our innate solubility is 1.25 if we're rounding, right? And our slope is 0.9816. Our correlation is perfect. So now we know our slope and our y-intercept, so we can figure out our Ka, can't we? We're going to use this to solve problems. So here's some drugs that we have that are on the market currently that use beta-cyclodextrins to improve water solubility. So you can see some of these, all these injections that need to have that invisibility cloak to work. Okay, that's it for beta.